I'm Joyce McGill, and today I'll be summarizing Richard Steiner's physics lecture on how the Planck constant is better than a kilogram artifact, or how the history of measuring physics constants will lead to a new international system of metric units. So the main issues that Dr. Steiner discussed were the problem with using old metric artifacts as a standard for measurement, and the movement toward more accurate metric measurements. In particular, Dr. Steiner discussed the erosion of the kilogram artifact over time due to chemical reactions with the cleaning agents. Obviously, this means that the measurement of a kilogram is changing with time, so we need to find a calculated constant value of the kilogram. I found this topic to be particularly interesting because I enjoy watching the scientific advances of mankind that have developed over the course of history and continue to evolve now. So, one proposed way of redefining the kilogram is the use of the Planck constant. Over time, this value, h, has become increasingly more accurate. We begin in 1900 with Max Planck, who used the constant h to explain the spectrum of a radiating body at some temperature. Then, in 1905, we have Einstein, who used h to explain the photoelectric effect. Then in 1913, Millikan combined known values to calculate h over E. However, in the 1960s, scientists discovered that he used a bad value for air viscosity, skewing his results. Then, in the late 1900s, Brian Josephson and Klaus von Klitzing made new quantum discoveries. These discoveries gave us the Josephson effect and the von Klitzing constant. These values are used in some of the more recent units used in modern times. These units were standardized in the 1990s. So you can see there's the Josephson effect, that we discussed, and then R is the von Klitzing constant. No, not the end. Okay. So today, scientists use a Watt balancing method of mechanical power over electrical power, as well as this equation, E squared over R is equal to h over 4 times F squared. These methods are used to calculate h. So, to return to the ideas presented on slide 1, we know that the kilogram artifact is changing over time. However, there are two proposed ways to give the kilogram a more exact measurement. One is Planck's constant, and the other is Avogadro's number. We know that the Planck constant has become more accurate over time. Using this method, the kilogram will be defined using Planck's constant as measured by the Watt balance method. The equation E equals hf, which relates Planck's constant to quantized energy, will be used first. This value can then be plugged into the next equation, E equals mc squared, relating energy to mass. If we combine these two equations and solve for mass, we'll get m equals F times h divided by c squared. Now the other method, using Avogadro's constant, wasn't really discussed in the lecture, so I decided to do a little research on the topic myself. Basically, the main argument used to support this method is that it's more accurate than using a man-made Watt balance apparatus, which varies from lab to lab. Basically, to keep it short, the values defined for this method use 1 atomic mass unit is equal to this really excruciatingly long fraction here, and 1 mole is exactly the second number down here. The reason cube values are used is because a cube is used to calculate the volume holding the molecules. So the cubes are because we use a cube. And that's the end. So I hope you learned a little bit about the movement to change the standardized measurement of a kilogram away from the kilogram artifact. Thank you.